Unit 5, friction. First of all, a little look at the laws of friction and what we can expect to encounter. So friction always opposes relative motion. The frictional force is always just sufficient to prevent relative motion up to a certain limiting value. Limiting friction acts at the moment when an object is said to be at the point of slipping. The limiting maximum value is proportional to the normal reaction between the surfaces in contact. The equation to find the limiting friction is this: F max, so that's friction, is mu r, where F max is limiting friction. Mu is the coefficient of friction. One of the best ways to think about it is the stickiness of the surface. So the higher mu is, the stickier the surface is. It's a bit like, you know, if I'm pushing, so here's an eraser. If I have this, or if I have a sharpener instead, it's much easier for me to push, for example, this than this, for a couple of reasons. This is lighter, but also this is a stickier surface because it's the rubber. So we have that, and then R is our normal reaction. The frictional force can be assumed to have a maximum value when motion occurs. Mu depends solely on the nature of surfaces in contact and not on the size or shape of the area in contact. Okay. Friction always opposes relative motion. Nice straightforward one here. If I'm pushing this, so with an acceleration this way, then the friction is going this way here. Frictional force is always just sufficient to prevent relative motion up to a certain limiting value. This is a complicated one. So you have to take my word for it that I'm currently pushing this rubber, but it's not moving. Okay, if I'm pushing with 1 Newton this way, it's giving back 1 Newton this way. Again, I'm going to push it a wee bit harder. Yeah, again, I have to take my word for that. So I'm pushing it with this pencil here, and it's just on the point of moving. I'm pushing with 2 Newtons here, and it's giving 2 Newtons back. If I push any harder, acceleration takes place. And the friction now is at maximum friction. It's given all it can to stop the motion. So it's going with 2 that way. But because I'm pushing with more than 2 Newtons, say 3 Newtons this way, then that's why it's moving in that direction there. It's quite hard to get your head around, but with a little bit of practice and doing some questions, we should be okay. Let's take a wee look at example 1. And we'll see how we get on. A body of mass 4.8 kilograms accelerating along a rough horizontal surface at 1.8 ms to minus 2 under the action of a 20 Newton horizontal force. Find the coefficient of friction. So it's horizontal, so with no inclined plane at the minute. So here is our diagram here, and it is accelerating. So we do our double arrow. Acceleration is 1.8, so we can fill that in. What's making it accelerate? It says this is a 20 Newton horizontal force heading this way here. What other forces are acting on this? We have our normal reaction. Doesn't affect the acceleration because it's going perpendicular, but that's okay. And then we have 4.8 G acting down this way, the mass times gravity. What's slowing it down is our friction, or our F max. Lots of different ways of writing this. Some people write FR, some people write F max, all totally fine. So there is acceleration taking place, so everything going this way doesn't equal everything going this way, and so we need to use then F equals ma. However, we can do everything going up equals everything going down because it's not bouncing up and down off the ground. So let's first of all resolve this direction here. Everything going up is R, everything going down is 4.8 G. Put that into your calculator nice and straightforward, 47.04 newtons. Going this way here, we have acceleration, so we use F equals ma. Again, I say this all the time. If it's in equilibrium, everything going this way equals everything going this way. It's not in equilibrium because there's acceleration, so we use F equals ma. 4.8 times 1.8. We're given both of those pieces of information. That's not normally the case, but that's okay. And what forces do we have? What's making it accelerate? The 20 newtons. And that's then take away the friction. We've been asked to work out the coefficient of friction, so we need to find mu. So we're going to do this wee bit first and find our friction. All right. So I'm going to take this over to this side and this over to this side. Hope you're okay with the crazy maths there. 20 take away 4.8 times 1.8. .8 times 1.8. equals, that's 8.64, 20 take away 8.64 equals 11.36. So my friction in this particular case is 11.36 newtons. That's my F max. If this was pulling with 11.36 newtons, the thing wouldn't move. It would just be about to move. If you pull with 11.37, it starts to accelerate. We're pulling with 20 here, which is more than this can cope with, so it started to move and started to accelerate. Anyway, F friction is mu R. 11.36 is mu times by R, which we worked out up above, 47.04. That means our mu is 11.36 divided by 47.4. Put in our calculator, I believe it's 0.241. That's the three significant figures. And generally, mu is sort of less than 1 on this. Things get a little bit weird.